Good morning.
Good morning again.
Morning.
Okay, let's see what we got here. Okay, ladies. Before we start, any questions? Anybody want to say anything? Nope. Okay. Oh, that's okay. As I promised. Well, we will. It's okay. Try to do the questions for chapter number 10 today. Right. Okay. Let's see this. Okay, the goals. Let's see. So let's go to page 157. And we made this okay. Have a diagram too. Oh, sorry, record too. Let's probably. Okay. And that's this. And what this one here is going to be is 9 millimeters. And then we have a beam. Oops. Like this. And then they mainly say that, okay, yes, this distance here, that is 8 centimeters. Now what we mean is, okay, just can say that this 9 millimeter here represent is going to be, yes, okay, the, okay, yes, okay. We say it's the size of PCT. Whereas, okay, as this 8 centimeters here, yes, okay, that is going to represent what we call, yes, okay, the focal depth, or which also could be called as, okay, the focal length. Okay, we mean that, okay, it's at a depth of 8 centimeters. That means, okay, we will have the focus. Is that clear? Now, girls, what you mean is, okay, you can see now the first question is, okay, what they say is, okay, what is the lateral resolution at a depth of 8 centimeters? So the main is, okay, as just indirectly, as okay, asking us, okay, what is going to be as, okay, now when we say lateral resolution, what that mean will mean is, okay, width of beam. And here they gave us, okay, as the depth, which is at 8 centimeters, right? Which we made, it says, okay, at 8 centimeters, what do we have? That's where we have the focus, as we just mentioned here. And what we already, as okay, would know in this instance here is, okay, that diameter at the focus is going to be, as okay, half the diameter or width of PCT, which is 9 millimeters. A half of 9 millimeters, that is going to be, as okay, 4.5 millimeters. Okay, so that will be, as okay, your lateral resolution at the focus, which is, okay, at a distance of 8 centimeters. Did that make sense? Okay, so this means, as okay, for also, okay, this means going to be, as okay, the numerical value of the lateral resolution for this beam here at a depth of 8 centimeters. Did you ladies get that?
Yes.
Right, okay. Now, what would that mean? That would mainly mean that, okay, yes, if the distance between, as okay, two structures lying side by side, if that distance is either equal to or greater than these 4.5 millimeters, that will lead to, yes, okay, to a good lateral resolution. Whereas this distance between, yes, okay, these side-by-side line structures is less than 4.5 millimeters, that will lead to a bad lateral resolution at this distance here, or of those two structures. Did you girls get that?
Yeah.
Yeah.
Okay. So you can mainly say, okay, whenever we talk lateral resolution, it's made as, okay, just another way of asking us, okay, what is the width of the diameter of the beam at, okay, as certain depths related to, yes, okay, the diagram given above, okay. So what they mean is, okay, just asking question number 2 is, okay, yes, what is the lateral resolution at a depth of 16 centimeters? Where we say, okay, this depth here is okay, that's the first 8 centimeters that where we have the focus. But then says, okay, what's going to be the depth at 16 centimeters? So that's going to, the lateral resolution at a depth of 16 centimeters, which is just twice your focal depth or focal length, which mainly is going to, as me, that's okay, indirectly asking us, okay, what is going to be as okay, the width of the beam at a depth of 16 centimeters, and that's again going to be 9 millimeters. Clear? Now this 6 centimeters goes here, okay, could also have been asked as twice the focal depth. Okay, so the wording of 6 centimeters here could have been also referred to as twice the focal depth, which was 8 centimeters. Yeah. But you can say, okay, it's pretty much okay, that's the same kind of questions that we had when we talked about the beam. Okay, yeah, okay, in that case, they say, okay, what's going to be the width or the diameter of the beam at whatever depths? Here they mean is, okay, just change that into lateral resolution. Is that clear, girls?
Yeah.
Good. Question number 3. Now again, yes, okay, where is the best estimate for the resolution at 4 centimeters? Now we can mainly say here, ladies, okay, yes, at the beginning of the beam, yes, okay, because that's okay, the width of the beam was going to be 9 millimeters. At a depth of 8 centimeters, yes, okay, the width of the beam was going to be, yes, okay, 4.5 millimeters, which is just half 9 millimeters. Okay, which is at, okay, so the depth of 8 centimeters. But what the main is, okay, asking us here is, okay, what is the best estimate of the, well, okay, lateral resolution at a depth of 4 centimeters. Clear? Okay, now here we can only, yes, okay, give an estimate. And the cheat is mainly, yes, okay, it's going to be a number that is going to be, yes, okay, less than 9 millimeters, but it's going to be greater than 4.5 millimeters. So any number that comes in between 9 millimeters and 4.5 millimeters is going to be, as okay, what the width of the beam in this case here would be at a depth of, okay, 4 centimeters. Okay, which we mainly says, okay, that is okay, would probably as okay be the best estimate for a lateral resolution at this depth here. Okay, so ladies, it can't be 1 centimeter because 1 centimeter that is actually is okay greater than 9 millimeters. As a matter of fact, okay, at that 1 centimeter is just okay as equal to 10 millimeters. Okay, it's probably not 9 millimeters because okay, that was okay as what the value was here. Okay, okay. 5 millimeters. Well, okay, we can say at least 5 millimeters. Yes, okay, meets one requirement. It is less than 9 millimeters and it's greater than 4.5 millimeters. Clear? It can't be 14 millimeters because 14 millimeters is going to be even greater than the widest part of the beam in the near zone. So the only one that made sense here, and it is just an estimate, is going to be as okay for 5 millimeters. Why? Because it meets the requirement of being less than 9 millimeters, but greater than 4.5. Clear? Okay. this depth here, yes, okay, it could still have been any other depth. We could say, yes, okay, let's say, yes, okay, at 6 centimeters. This would be, still have been an answer. Clear, because after all, is it just okay, yes, and an estimate. Okay, so the only thing we can, or it would be able to say, well, okay, it's going to be lesser than this, but greater than this. Did that make any sense?
Yes, it did.
Okay. Let's just go to the slide so we can make it okay. This structure, okay, yes, reproduce this thing here. And we see it's okay. That's on 9 millimeter. Oops. Okay, that's why we have our beam and we say it's okay, this distance here was okay, yes, 8 centimeters. Now again, it's okay. What is the best estimate for the resolution at a depth of 7 centimeters? So he says, okay, this was at 8 centimeters, and okay, here it was 4.5 millimeters. Now they just say, as okay, ask the same question as okay, what is the best estimate for the resolution at a depth of 7 centimeters? And it's the same concept goes, because it's only as estimate. It's going to be a number that is less than 9 millimeters, but greater than 4.5 millimeters. So the option that we have here is still the same: 1 centimeter or 10 millimeters, 9 millimeters, 5 millimeters, and 14 millimeters. Clear. So the one that is okay, still is okay, only is okay, meet that requirement is 5 millimeters. Did that make any sense?
Yes.
Good. Question number 5. Now, okay, yes, what is the best estimate for the resolution at a depth of 21 centimeters? Which probably is okay, will be somewhere out here. We says, okay, if this was 8 centimeters, we can take another 8 centimeters and say, yes, okay. We could say that's okay, another 8 centimeters, say, okay. There's another, so this becomes a total of 16 centimeters. Okay, we can still say it's okay, another 5 centimeters. So this may, yes, okay, become okay as an estimated of 21 centimeters. Now, what numbers do we have? We have 1 centimeter, we have 9 millimeters, we have 5 millimeters, and we have 14 millimeters. Now, primarily as okay, we should say as okay, first of all, as okay, it can only be a number that is going to be greater than 9 millimeters. Because that's what's called the diameter of, yes, okay, lateral resolution is going to be at a depth of 16 centimeters, which was twice your focal depth. Clear. So pretty much okay, as any number that will be greater than what you can call it, 9 millimeters. Okay, now we can go here and say, okay, this would be as okay, 10 centimeter or 1 millimeter. Oh, sorry, 10 millimeters, sorry, or 1 centimeter. Okay, but since the went, yes, okay, far beyond that, that's why we can, yes, okay, go and say, it's okay, 14 millimeters. Or most likely, it's okay, be the best estimate for the lateral resolution of the beam at a depth of 21 centimeters. Did you ladies get that?
Yes.
Okay, let's see. So yes, okay, these questions here are mainly yes, okay, in reference to yes, okay, to a diagram. No, they mean yes, okay, just asking yes, okay, questions and yes, okay, verbally. Clear? Okay, so the ability to distinguish two structures that are lying close together is called resolution. Mainly as okay, just a repeat question from what we had when we did exit resolution. The same question was asked then. Clear? Okay. Now, okay, the ability to distinguish, okay, question number 7 is okay, the ability to distinguish two structures that are lying close together. But that's resolution, but then there's okay, they specify close together how? Front to back. Now that front to back, that kind of is okay, resolution is going to be called exit resolution. And as I said, yes, okay, what you guys have to, yes, okay, get used to is that some, yes, okay, characteristics, parameters, etc., may be known by more than one term. So you still have to remember there was also called, yes, okay, a longitudinal resolution. We also call this one here, yes, okay, a range resolution. We also call this one here, yes, okay, a radial resolution. And we still call it, okay, as a depth resolution. Clear? Okay. But the thing about it is that, okay, it's going to, yes, okay, we refer to either as, okay, front to back, or this front to back can also be called, referred to also, okay, described as parallel to the beam's main X. So that kind of resolution where we refer to as a exit resolution. Clear? Question number 8. Now the ability to distinguish two structures lying close together. So once you see that, okay, yes, the first thing you should catch into your mind is going to yes, okay, Dalbert and yes, okay, resolution. And even yes, okay, at this point, as you can say, yes, okay, lying close together. That kind of wording mainly yes, okay, will specify that, okay, yes, they're talking about, okay, yes, a spatial resolution, which is going to yes, okay, then be measured in okay as a unit of distance. Close together, far from one another, something like that. So that's okay. I mean, it's okay that the distance between them is close. Okay, but here it's okay again. They specify as okay, close together in one way, side to side. So, ladies, this side to side here, yes, okay, that is volume. Okay, yes, okay, will be yes, okay, the magical term for yes, okay, for your lateral resolution, which we then still yes, okay, refer to as the angular resolution. We even say it's okay, transverse resolution, or it's okay, the azimuthal resolution. Clear? Or this side to side here could also be referred to as being as okay, perpendicular to the beam's main axis. And ladies, mainly because okay, they are talking about okay, being perpendicular That's why it's okay. This resolution here is also known as the transverse resolution. Did you girls get that? So parallel to the beam's main axis is axial resolution. Perpendicular to the beam's main axis is going to be what we call the lateral resolution. Yeah. Any questions? Okay, but please keep in mind, ladies, you may not necessarily get the word lateral resolution as an option. You can begin as okay angular, you can begin as muted, you can begin as okay transverse resolution. Likewise, okay, for your axial resolution, it's not a must that I have to give you goals. That's okay. The term axial resolution as an option. I may, yes, okay, give the very same question, but it's okay, give this as an option, which may be correct. The range, the radial, or the depth resolution. Clear?
Clear.
Good. Now, ladies, as I said earlier, we call these kind of resolutions here, it's okay, spatial resolutions because they are resolutions in pertaining to space, or yes, okay, distance, or something that can measure, yes, okay, be measured using the unit of distance. And that's me, yes, okay, what your question 9 all is about. Okay, axial resolution and lateral resolution are both measured with the unit of distance. Now, that's okay, we can measure it in terms of centimeters. It can be as okay, millimeters. Nobody says that you can't, yes, okay, express it in micrometers. Okay, there's nobody who can say, well, okay, you can't express it in, okay, decimeters. Or it's okay that you can't express it in meters. Okay, but if you said, okay, as if centimeter, if you take that as that, okay, the common standard, what you mainly will get is, okay, if you express the value in centimeter, let's say it's okay, 2 centimeters, and you want to express that in millimeters, that is going to be equal to, yes, okay, 20 millimeters. Clear? Okay. That same 2 centimeters, which is 20 millimeters, is going to be, yes, okay, the same as 20,000 micrometers. Clear? And you can say, it's okay, that 2 centimeters, if you express that in decimeters, that's going to be 0.2 decimeters. Or that 2 centimeters is going to be equal to 0.02 meters. And so on. So practically, yes, okay, all these numbers here are equal to 2 centimeters, for instance. Okay. And boy, yes, okay, your lateral resolution, which is side to side. And okay, yes, axial resolution, which is front to back, or what we can say is okay, superficial leap, is going to be, it's okay, expressed in terms of using a unit of distance. Did that make sense? And that's why we call them spatial. Okay. I, yes, okay, introduce you girls to, yes, okay, the term spatial when we did our intensities. Okay. At that point, we said, okay, what was your spatial intensity? I mean, it's okay, that's the intensity. It's okay, because that's okay, an area of the beam. But okay, you still measure it, okay, it's in some sort of, okay, it's physical or distance-wise measurement. Whereas you said temporal, that was going to be as okay pertaining to time. Okay. At what time in the pulse did we have the greatest intensity? That was already called the temporal peak. Yeah. So you will see that, okay, there's a lot of things. We're going to come across this again and again and again and again. So whenever you use the word spatial, you will say, well, okay, this is an object that measures this much and this much physically. Okay. Or you can say, okay, in area or space, something that you can refer to as that is going to be as okay considered a spatial type of that thing. Where, okay, when it goes time, then it's going to be as okay temporal. Clear? Okay. And okay, as things may change in the course of time. Okay. So that's okay. These two terms, they are going to just okay be repeatedly used again and again and again and again. Okay, we saw them in intensities. We are seeing them here in resolutions. Well, you haven't got to the temporal resolutions yet. But again, as okay, in a later chapter, there's going to be something else that is again going to be referred to as, okay, temporal type and spatial type, or whatever topic we're discussing then. Okay, ladies, so please make sure that you are clear about those. Any questions? Okay, so that's okay. Then temporal here is okay. It doesn't mean the bone or the lobe of the brain. It is going to be as okay pertaining to time. Question number 10. Now, when the number of cycles in a pulse increases, while the frequency remains the same, the numerical value of your range resolution. Now, what do they do here? What they say was that, okay, yes, let's just do this as, okay, yes, E, B. That remains says, okay, from A to B. What is it that we do? We increase. Okay, so what's going to just increase is, okay, the number of, is okay, cycles per pulse. That increases. Whereas, okay, at the other end, it says that the frequency remains the same. Then they can just, okay, just ask, what is going to, yes, okay, what is going to be the effect on the range resolution? Clear? And you can already see, it's okay, what did range resolution mean? That was just another name for it, okay, what we call the axial resolution. But if you don't know that, you will be LOST. Clear? Now, what does it mean to have, yes, okay, same frequency? That indirectly, yes, okay, just means that, okay, the wavelengths, it's all the same. Clear? But the main, yes, okay, just ask as what happens to the numerical value of your range resolution or exit resolution. Now, let's just take as, okay, hypothetical numbers, and we can say, okay, here's, okay, we had, for instance, 3 cycles per pulse. We increase that to, let's say, as okay, let's just say that we increase it to 6. Nobody know. 6 cycles per pulse. You can mainly say as okay, now since the frequency was the same, the wavelength will also be the same. So we can just say as okay, let's just keep the wavelength and say as okay, 3 millimeters. So for A, our calculation comes down to 3 times 3, right? Which may mean that, okay, as our spatial pulse line will be equal to, as okay, 3 times 3, which is 9 millimeters. Here, yes, okay, you were for B. It becomes 6 times 3. 6 cycles. Each cycle has, okay, as a wavelength of 3 millimeters. So it's okay, here we can make it, okay, the spatial pulse line becomes, 18 millimeters. Now, if somebody still, yes, okay, wants to calculate, yes, okay, the numerical value, we can say, yes, okay, here's, okay, the numerical value is going to be 9 divided by 2, which becomes 4.5 millimeters. Here's going to be, yes, okay, 18 divided by 2, which becomes 9 millimeters. But we can mainly say, okay, since, yes, okay, we increase the number of pulses, yes, okay, the numerical value or the range resolution will increase. Did that make sense? Had it been the same question, but yes, okay, where this is, okay, if the number of cycles per pulse decreases, then you can mainly say, okay, the numerical value would then have decreased. Clear? Okay. Now we can say is, okay, if the cycles remain the same, but if the wavelength is, let's say, is okay, increased. If the wavelength, for instance, okay, was increased, right? Because yes, okay, 5 millimeters, it was going to become the same. Yes, okay, that okay, as the numerical value would increase. Or if we went in the opposite direction and says, okay, that the wavelength decreased from, let's say, 5 to 3, well, okay, yes, then the numerical value will decrease as well. Clear? Okay. So that's okay. These numbers, this is me, that's okay. I just made put them there, yes, okay, mean it just says, okay, well, okay, this is how you actually, as okay, may look at it, okay, as numerically wise. But it all is okay, is coming down to the relationships. So if you know your relationships, that's okay, what is the relationship to of the number of pulses, or number of cycles per pulse to your range resolution's numerical value? Right, okay. Please keep in mind here, okay, they put the word numerical value in the question. What is the relationship? Yes, okay, let's say the wavelength or frequency to, yes, okay, the numerical value of your range resolution. Clear? Okay. Now, the reason that they put these two things is, okay, number of cycles and frequency, because, okay, they have already mentioned those in the chapter. Where it says, okay, number of cycles that are what we call ringing. And we always say, it's okay, frequency, and it's okay as a relationship to the resolution. Clear? But keep in mind, guys, that's okay, they mentioned the word numerical value. So you can mean that's okay. Greater numerical value will lead to, yes, okay, a poor resolution. So this one here is okay, that will be, it's okay, a poor resolution because of the greater numerical value. But the greater numerical value increases because we increase the number of cycles. Or we could say, okay, more ringing. Clear, where, okay, they say, well, their frequency is the same. So it's okay, from that you can mean it's okay, just presume that, okay, the wavelength is the same. Or you can say, okay, but then, you know, the greater the frequency, well, okay, yes, the lower the wavelength. The lower the wavelength, well, okay, yes, your mean says, okay, that will mean is okay, lead to a lower numerical value. Lower numerical value means okay, will give you, yes, okay, a better resolution. Did you ladies get that? Or is somebody still miss, okay, or is somebody still missing out between numerical value and resolution?
I have a question.
Go ahead.
So if the frequency increases, the wavelength decreases.
Yeah.
But
so if the wavelength, okay, go ahead.
But what happens if the frequency decreases and the wavelength increases? Does that make less ringing?
No, ringing has nothing to do with that. I told you guys, ringing mainly is okay, just another word for it. Okay, it says okay, the number of cycles. And I even gave an example of saying it's okay, the time that your phone rings before you pick it up. You can mean it says okay, each time your side is okay, phone ring, you can say okay, that is one cycle completed of your ringtone being played, right? So if you can let it go on, ring, 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 what happens? That'll be more ringing compared to ring, ring. Okay, you can say that will be less ringing because it only has okay rang twice. So that's okay. The phrase here is okay of ringing mainly is okay, just means how many cycles are there in a pulse. So less, that may mean that okay as less number of cycles. More number of cycles. Clear? Then the next thing comes, okay, yes, what is your frequency? Now, the reason that they used, the reason that they use the word frequency is okay in this question here, because, okay, what your book says for resolution. Or we can mean it's okay for, or we can just, okay, so we can say it's okay for good resolution. Prime is okay, good what resolution? Well, okay, it's exit resolution. What did we need for a good exit resolution? We needed less ringing. Which we may just say as okay, that will be as okay, a low number of cycles per pulse. The other thing that we needed for yes, okay, good exit resolution. As your book mentioned, is going to be as okay, a high frequency. Did that make sense? Now, what we indirectly as okay can take from as okay from this high frequency mainly or mean that we will have a low wavelength. And what was okay, yes, your numerical value for the exit resolution. That was mainly as okay, your spatial pulse length. Just says okay, here it's okay divided by 2. But how do we calculate just okay this spatial pulse length here, or the actual is okay, the numerical value of your exit resolution? There's a spatial pulse length divided by 2. How do we calculate just okay the spatial pulse length? It was nothing but your number of cycles, which is okay was multiplied by the wavelength. Now, my dear, if both of these just okay are kept low, 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 what do you get? You will have okay as a short spatial pulse length. And okay, as if you divide that by 2, you will get okay as an even smaller as okay numerical value of the exit resolution. Which may mean that okay, yes, this would be better or best. Whereas okay, if you go the other way and say that if we do the opposite, for instance, says okay, more ringing, which means okay, would just mean okay that we have a high number of cycles per pulse. And or if we say it's okay that we have a low frequency. As this low frequency is okay, mean the same as saying it's okay, we have pulses with a great wavelength. Now, when you check this high number, great number of pulses, cycles, and or yes, okay, multiply that by a great wavelength. What do you get? A great spatial pulse length. And here, yes, okay, if you divide that by 2, yes, okay, you will still get, okay, as a greater numerical value of the axial resolution. Where this great numerical value of the axial resolution will lead it to be, yes, okay, poorer. Or the axial resolution to be poor. Right? What they made is, okay, just did in the question say, well, okay, we keep frequency the same. Frequency don't change. Did that make sense? The only thing that we changed was number of pulses. Or number of cycles per pulse. That is increased. So if that increases, what's going to happen? The numerical value of your, okay, as your axial resolution, or as they said here, as okay, range resolution is also going to increase. That's all they asked. Now you can be given as okay, the same data. Okay, when we say it's okay, when the number of cycles in a pulse increases while the frequency remains the same, the range resolution is going to be improved, degraded, or remain the same. Now, since that's okay, that we don't ask of the numerical value, but rather says okay, where it's going to be is okay, the effect of increasing the number of pulses. Or yes, okay, the range resolution. That's going to just okay get degraded. Although yes, okay, we keep the frequency the same, but just by increasing the number of pulses. Well, we can say okay, that will lead to an increase in the value, yes, okay, numerical value. That increase in the numerical value actually will cause the resolution to degrade. What's resolution? Yes, okay, here they use the word range resolution. You can be bombarded with the same question, yes, okay, using the term axial resolution, radial resolution, longitudinal resolution, or depth resolution. Clear? If they said, well, okay, yes. If you do it this way, I say it's okay that the number of pulses remain the same. Not the number of pulses, sorry, number of cycles remain the same. And okay, yes, we increase the frequency. Clear? Okay, what's going to be as okay, the effect on the numerical value of radial resolution.
Is it going to decrease?
It will decrease, right? Because this increasing of, let's say it's okay, the frequency indirectly means okay, the wavelength will decrease. So the numerical value of the radial resolution, yes, okay, that will also decrease. And that decrease in the numerical value of the radial resolution or range or axial or longitudinal or depth mainly will mean that okay, yes, the resolution will improve. Did that make sense? Did that
Yeah.
make sense?
It does.
Yeah, okay, good. Let's see about that. So let's go to the next question. Yeah. Now, when the number of cycles in a pulse increases, no, okay. So because, okay, we increasing the number of cycles in the pulse. And here the is okay, put in bracket, which means okay, that will mean okay that there's going to be more ringing. Okay, while the frequency remains the same. So frequency is okay, remains the same. Okay. The image quality, okay, quality is probably okay, another right word to use, but anyway, improves, degrades, or remain the same. Now we can say it's okay, frequency remains the same. That means it will indirectly mean that okay, as wavelength remains the same. Now that's okay, when we increase the number of cycles in a pulse, that will mean more ringing. Okay. What we can say is okay, the product of okay as this greater number of cycles, all this okay multiplied by the same wavelength will lead to that okay as the that is going to be an increase in the numerical value of the range resolution. Yeah. But what they may is okay, just ask you about here is okay, what is going to be the effect of increasing the number of cycles in the pulse on is okay the resolution. Now you can make since the numerical value increases, that's meaning going to cause the resolution here to decrease. Or we can say it's okay, get degraded. Did that make sense?
Yes.
Okay. Because what does that increase of the numerical value mean? That is okay, we'll need okay as a greater distance. That we will need okay as a greater distance between these two structures here to be as okay distinctly shown on a scan. Okay, where it can mean okay, yes, okay, the relation of these two structures to one another is going to be as okay, front to back, or parallel to yes, okay, beams, main axis. Yep. Any doubts, ladies? So all yes, okay, comes down to yes, okay, to the resolute yes, okay, relationships. Sorry. But then you also have to yes, okay, you gotta be watchful because okay, question 10 and 11 may look the same. Okay, but in one case, it's okay, they ask about, it's okay, the numerical value. And the other they ask about, that's okay. Same scenario, that's okay, but its effect on the resolution. So those effects are going to be as okay opposite to one another. Question number 10. Oh, sorry, 12. And what they mean is okay, just asking us is okay, high or low frequency. Transducers have the best. And what is the word that they use here? It's okay, range resolution. No, ladies. What was range resolution? It's what we call exit resolution. What did we need for SOK, the best exit resolution? Directly written in the book. For best exit resolution, you will need a high frequency transducer. But not too high, because too high is going to cause, what is too high of a transducer going to lead to?
Attenuation.
Attenuation. Clear? Okay. Good. So that's okay. But you can be asked opposite. Okay, where you can say, okay, low frequency transducer, what is that going to lead? That's going to lead to, that's okay. You can say, it's okay, a poor range resolution. Now name the 4 synonyms for exit resolution. Clear? And 13 is okay, the longitudinal number, or sorry, lucky number. Was that okay? Yes. We call it longitudinal. Okay, okay, why not? Longitudinal. We call it range. We call it radial. And depth. And of course, yes, okay, we had axial. But these just okay, what the other 4 synonyms for your axial resolution. Question 14 is just the opposite, or it's okay, the same, but just asking about it's okay, your lateral resolution, which was angular transverse and okay, yes, azimuthal. Yeah. Question 18, not 15, sorry. Now the pulse length is 8 millimeters. What is the minimum distance between two reflectors positioned one in front and of the other that still reproduces two echoes in your image? So what they mean is, okay, with this pulse here, where it has a length of 8 millimeters. Let's just say, okay, as we measure our pulse. And say, yes, okay, it is 8 millimeters long. They may be asking us, okay, what's going to be as okay the minimum distance between two structures? Line, yes, okay, front to back. So where is the minimum distance? That's still was okay, cause these two reflectors or these two structures here to show up as, we can say it's okay, two structures on our image. And the only thing that we needed was, okay, yes, what is the half of the pulse length here? Okay. Now you should make it as okay, be able to say as okay, since the use is okay, unit of distance is okay, that makes this here the spatial pulse length. That's okay, this is your spatial pulse length. So what do? We mean it's okay, just divide that by 2. So our answer is that we have, okay, as we'll need at least a distance of 4 millimeters between these two structures here for them to be shown as 2 separate echoes on the image. Clear? Okay. So why did they use the word echoes? Echoes is means okay, just another word for a reflection. So that we see is okay, these two structures here as 2 separate echoes or 2 separate reflections or structures on the image. So don't go and say, well, okay, didn't mention anything about it. Okay, this being is okay, an examination of the heart. Because some of you may think, okay, as echocardiograph. Every ultrasound is produced by echoes. What your machine or what your system is going to use to create the image with is the reflections that it receives. Where do those reflections come from? Is there anybody who can tell me, yes, okay, where does those reflections come from?
Doesn't it reflect off the structure? It reflects from the structure.
It reflects off the structures, right? Okay. And those structures being shown on the picture or image, that's your ultrasound. Clear? Okay. So that's okay. The word reflection is mainly it's okay, just replaced by echo. But here is okay, we need to say it's okay. The spatial pulse length. Now you can be given it directly as this and say, well, okay, yes, your spatial pulse length or pulse length is this many millimeters, centimeters, whatsoever. Right? Okay. Or you can be given, yes, okay, and say, well, okay, well, we have a pulse. This pulse here has this many cycles. Clear? And okay, yes, they have a wavelength of, let's say, this much. Okay, then the first thing you would need to do in that instance is, okay, at least calculate out your spatial pulse length. How do you do that? Multiply those two. And then you divide that spatial pulse length by 2. Okay. But that will only, as okay, only help you to determine as okay what the distance between two structures has to be as okay where those two structures lie in front or behind back to one another. And here it said side to side instead of front to back. You can't determine that, because that's going to be determined by as okay the width of your beam. So the width of your beam is going to is okay determine what the distance you will need to have between two structures lying side to side. Clear? How would you get that? They had to give you okay some information that talks about is okay how wide is it that the beam is. You don't have that. Did that make sense? So watch out for is okay terms such as back to front or front to back or side to side. Or parallel to the main axis or perpendicular to the main axis. Because the first one's main yes okay refers to yes okay your axial resolution. Second one's lateral resolution. Okay, girls. Now, what do we have in the back of the book? An exam review from, okay, let me write that down. Oh, that's going to be, okay, your task for the next couple of minutes. You can mainly says, okay, from page 477 to page 490. You mainly have questions from 258 to question 274. And ladies, these are questions about, yes, okay, your axial resolution. Now just take, okay, yes, 10 minutes to refresh your coffee, smoke your cigars or whatever. And then you have, okay, it's 20 minutes to come and, okay, try to solve these questions here by yourselves without looking at the answers. You can always verify your answers once you have answered it. Clear? And when we come back, yes, okay, we can play our little focus. Yes, okay, try to answer, yes, okay, why the answers are the way that they are. But then also, it's okay, play a little around with the question and say, okay, now if this was asked this way, then the answer would have been this. Okay. So is it fair that I say that I see you girls back at 10:50?
Yeah.
Okay, have fun till then. Back. Okay. Okay, boss. Is everybody there?
Yes.
Good. So we can say yes, okay, question 258. That's where we started from. Now let's see. Now the EXA resolution describes the accuracy related to visualizing two structures that are dashed to the sound beam's main axis. So the chart that you need to put here is either going to be parallel, perpendicular, oblique, or normal. Clear? Okay. And for your EXA resolution, it had to be parallel to the beam's main axis. Question number 259. Now you are purchasing, okay, as a diagnostic ultrasound system. Okay, good. Now system X. Okay, now has a regular resolution of 0.7 millimeters. So it is okay, 0.7 millimeters. Yeah, system D has a, okay, system D has an axial resolution of 0.4 millimeters. Clear? Based on this information, which will produce the better quality picture. Now goes, although not directly mentioned in the question, but this value here and this value here, these are meaning that's okay, the axial resolutions, numerical values. Did that make sense? Now what they mainly ask us is, okay, which of these two is, okay, will produce the best axial resolution? And that was going to be, as okay, the one with the lowest numerical value, which would be C, or which would be system D. Did that make sense?
Yeah.
Clear? Okay. Whereas, okay, as of these two systems here, as okay, the one that will produce, as okay, we can say the worst or the poorest axial resolution, that will be in system X. Okay. So you probably, as okay, will like to, as okay, purchase this one here. Okay. Anyways, good. Now, okay, sorry. Maybe I should do it this way. Now they may say, okay, these are the axial resolutions. Now, what you also could be done, or what also could be asked is, they say, okay, these are the two systems, and they may ask you, yes, okay, what is the SPL of, okay, and they can go with either systems, right? Okay. System X. And, well, okay, yes. System D. Now, how would you get what the spatial pulse line would be? for system X, W is okay, there's 0.7 to multiply by 2. So if you can say it's okay, 1.4 centimeters or 14 millimeters. Whereas for system D, as a dolly, it will be as okay, there's 0.4 multiplied by 2, which then will become, because okay, 0.8 millimeters. Did that make sense? Okay. So you can be asked any crazy thing, right? Based on, yes, okay. Yes, okay, this information here. Question 260. Now, the axial resolution of an imaging system is reported to be as okay 0.85 millimeters. So you guess it's okay. The axial resolution of a system is going to as okay be 0.85 millimeters at the beam's focus. Clear? Now, what is the closest estimate of the system's radial resolution at a location 5 centimeters deeper to that focus? Now, let's just see what that means. Now, what they mainly say is, okay, let's say that we have okay, as a focus, or we have a beam. Because that's what they are asking us. This is your beam. Right? Let's just say that, okay, as we have a focal depth. Or let's just, okay, let's say 6 centimeters. Now, what they mainly say that our axial resolution is at this depth here is 0.85 millimeters. Right, okay. Yeah, they mainly as okay, then just ask us, okay, what is going to be as okay, the axial resolution at a depth which is, that's okay, 5 centimeters deeper than the focus. So they may as okay say, but there they say, okay, what is the radial resolution, which is just okay as another name for your axial resolution. Yes, girls. What would be the answer? And why? Yes, ladies.
I don't want to be annoying, but can you just say the question again?
It's question 260.
Oh,
Oh,
it's B.
I don't know what B is.
Oh, equals to 0.85 millimeters.
Or why?
Because the axle resolution remains the same. It can't be changed.
It remains the same, right? Okay. It would have been a different question, or it would have been a different thing had they asked off the range. Yes, okay, because there's okay lateral resolution. Then it would have changed. Because says okay, it was going to be as okay, the numerical value would have been greater than 8.5 millimeters. Okay. But it's okay, here they really is okay, played around with it, okay, not just the factor that okay, yes, exit resolution also was called range resolution. Okay, and neither of these, or okay, we can say neither of these is going to be as okay determined, or we can say okay equal to the beam's diameter, but rather yes, okay, the spatial pulse length. Maybe you can say it's okay, the spatial pulse length will be as okay 17 millimeters, but that's going to remain 17 millimeters here. It is going to be 17 millimeters even at this depth. Is going to yes, okay, be 17 millimeters even at this depth. And as a matter of fact, even as okay, 17 millimeters at a depth that is 5 centimeters beyond the focus. Did that make sense?
Yes.
Okay. So yes, okay, here they played around with a lot of things. So it's okay, if you didn't have your concepts intact, that's okay, you would be lost. Now, question 261. Now, yes, okay, the information that we are given here is okay, a little bit too early. So, two systems undergo an evaluation. Yes, okay, one system has, okay, has 1 million pixels. Okay, okay, this question is going to be as okay, more relevant after we have done chapter 15. Because that's made as okay, we will talk about things such as what do you want to call it? Actually, it's okay. Spatial resolution, which will be as okay, pixels and pixel density and things like that. Okay, so this question here is for yes, okay, chapter 15 to be more accurate. So let's just go on to the next one, which is 262. So again, yes, okay, true or false. Now, the lower the numerical value of longitudinal resolution, the worse is the picture. That's false. Because we already know that, okay, so if we have a lower numerical value, that lower numerical value actually is okay, will lead to is okay, better exit resolution, or what in this case here, okay, said what's going to be, it's okay, the longitudinal resolution. So that's false. It's going to be that lower numerical value, that's okay. The reverse picture, yeah, okay. Reverse picture, sorry. What the hell? Because I had they're gone the opposite, I say it's okay. Greater numerical value had been worse, yes, okay, that would have been true. Okay, we can mean it says okay, lower numerical value. If we have a lower numerical value, that is going to, yes, okay. I guess it's okay, make a better picture. That would have been true as well. But lower numerical value, it's okay, makes a better picture. Higher numerical value makes it worse. Question number 263. And knowingly or unknowingly, that's okay, what I tried to explain. Okay. So let's see. One way that the sonographer can alter the exit resolution achieved during an examination is to adjust the maximum depth of image. That is not going to affect your image as okay, exit resolution. Because okay, the AR or exit resolution is going to be the same whether you look at 1 centimeter depth of a picture, whether you have a picture of an image of 2 centimeters depth, or whether it's okay, it is, let's say 3 centimeters deep. Your exit resolution is going to remain the same. Clear? Okay. Did that make sense?
Yes.
Even, yes, okay, even if it was the same question that they had asked, sorry. That's okay, yes, okay, the same thing is okay about the lateral resolution. It will still be false. Because your lateral resolution does not change by you changing the depth of the image. Okay, so please goals, yes, okay. Because lateral resolution, yes, okay, that was going to, yes, okay, we can say it's okay, dependent upon the focal depth or focal point or focal length. Okay. And focal depth or focal length is not the same as depth of image. Clear? Okay. Depth of image, that word V is okay, may change. If you, for instance, okay, go from, let's okay, as an image depth of 1 centimeter to, let's say as okay, 6 centimeters. That's where we actually is okay, change the depth of image. Where we may say as okay, focal depth. 1 centimeter is probably too low. Let's just take, let's say 3 centimeters. Okay. Because okay, at a 3 centimeter depth of image, you may still be able to, yes, okay, focus at a depth of 2 centimeters. Likewise, yes, okay, you may still be able to, yes, okay, focus at a depth of 2 centimeters. What does that mean? That means that, okay, at this point, yes, okay, of 2 centimeters, yes, okay, your beam is at its narrowest. How was that focusing achieved? It required to be fixed because the transducer itself had a focal depth of 2 centimeters. Or it could be, yes, okay, electronic. That we mean is, well, okay, we want the system to focus at a depth of 2 centimeters. So it's going to be at this focus here that we will have the best lateral resolution. Okay, goals. So you changing, yes, okay, the depth of image is not going to affect your focal depth, and vice versa. Okay, so there is a difference between the two. So they are not the same thing. Is that clear? So if you mess up with that, yes, okay, it's easy to understand, or it's okay, easy to get correct. But also, yes, okay, evenly and equally easy to get wrong if you don't know the difference between the two. Okay, so mainly that's okay, adjusting on that knob that says depth. That's just going to just okay, make your image deeper and deeper and deeper. Or you can say okay, that you will be able to just okay, visualize or scan to yes, okay, a greater and greater and greater, or lesser depth. But you can increase the depth as much as you want and still says, okay, so like I still want the focus to be at, let's say, 3 centimeters. You can take it from 5 centimeters to 8 centimeters, 10 centimeters, 12 centimeters, 16 centimeters, but still be focusing at a depth of 2 centimeters. Did that make sense? Okay. Question number 250 or 264. So that's okay. For 263, well, we can say that's okay. The only way that you actually be able to just okay adjust your resolution or exit resolution is okay as either increase the frequency. Right. And or that's okay to use another transducer. Because primarily that's okay your spatial pulse length in this instance, yes, okay, or for your lateral exit resolution, sorry, will be as okay determined by the source, which in this case, yes, okay, will be your transducer. Question 264. Again, yes, okay, true or false. So when a specific sonograph ultrasound system and transducer, or with a specific ultrasound system and transducer, the system axial resolution is invariant, and the sonographer cannot do anything to improve it. Now goes two things here. Okay, that's all that's okay. This statement is true. Why true? Because okay, this is okay, a specific ultrasound system. Clear, and the even went on and say that's okay, specific transducer. Which means, well, okay, this specific system and transducer, that's okay, then your SPL is invariant. That's okay. The SPL or spatial pulse length is invariant. Invariant is okay, just means another word for yes, okay, not changeable. Or as you may have said, it's okay, not adjustable. So the only way by which we could, yes, okay, change the SPL or change, yes, okay, the exit resolution was if we, yes, okay, get off this specific system as, okay, use any system or any transducer. Did you ladies get that?
Yes.
So had it said any system but not specific, then it would have been false because it's okay. Then you can change. Clear? Okay, but maybe it's okay because now specifically it's okay, this transducer with this system, this remains non-changeable. Because for you to change this, you either most likely it's okay, will have to change your transducer, or in the worst case scenario, okay, use another system. Question 265. Again, true and false. So is it true that say it's okay that a shorter pulse leads to it's okay better image? Now, better is probably not the best option or better picture because it says okay, more accurate, or because I said greater resolution. That's true. Shorter pulses in what term? Mainly as okay, shorter SPL. Okay, which mainly as okay will lead to as okay a lower numerical value of that's okay in this case it's okay your exit resolution. But lower numerical value is okay better image. Or you can say it's okay greater accuracy or better resolution. Whereas if any of these two, we could say as okay, greater pulse leading to better image, that would be false. Or if you said shorter pulse leading to yes, okay, worse image or degraded image, or it's okay, degraded resolution, that will also have been false. Clear? Question 266. Now, ultrasound pulse has a pulse repetition period of 1.2 milliseconds. Please keep in mind here, it's okay, you are giving us okay the pulse repetition period, not the pulse duration. So that's okay, there's a 0.2 1.2 or 1.2 milliseconds. And a spatial pulse length of, okay, yes, 2 millimeters. And okay, yes, it says, okay, it has a wavelength of 0.4 millimeters. What is the axial resolution of the system? So let me ask, okay, this is, okay, what is the axial resolution? Now you can mainly say as, okay, goals, this information here is, okay, it was just blah, blah, blah. You didn't really need it. You can even say as, okay, you didn't really need this information as well. Because the only information that you needed here was this. Where you can say, okay, now if our SPL is, or spatial pulse length is 2 millimeters, then the axial resolution's numerical value is going to be what? These 2 millimeters here is, okay, divided by 2, which becomes 1 millimeter. So how many meter, okay, at this system here with this spatial pulse length, if the distance between this reflector and this reflector, if that distance was at least 1 millimeter, you will have a good axial resolution. If this distance here between these two reflectors here was lesser than 1 millimeter, let's say it's okay, for instance, okay, 0.1 millimeter, or which actually is going to be, okay, 1/10 of a millimeter. Then you will have had a bad axial resolution. Because then what these two structures here not had been shown as two separate reflectors on your image. Is that clear?
Yes.
Okay. Question number 267. And again, it's okay, true or false. Sinka. More cycle, okay, the more cycles there are in a pulse, okay, the greater detail will be visualized on an ultrasound scan. I will lead to that's okay. Greater details in ultrasound scan. That is false. No, that's okay. Here is okay. What they mainly is okay just mean by greater details. We can say it's okay. Greater accuracy. But that becomes false because for that greater accuracy is okay, we will actually need a lower numerical value of the, well, okay, we can say in this case, it's okay, axial resolution. How do we get that lower numerical value? Which would have, yes, okay, being greater accuracy. or it's okay, more details. That is if our pulse had less number of cycles. Or they may as okay replace the phrase here as okay, great number of cycles in a pulse. That can be replaced by as okay, more ringing. Clear, which mean as okay, cause that okay as sorry, the less number of cycles per pulse will actually have been less ringing. But they probably as okay choose the word as okay, greater number of cycles per pulse. Because okay, people who wrote the text was says okay. Now be okay, yes. Or have been more ringing. So that's okay. Please remember, goals, that's okay. That the number of cycles per pulse, that is what we'll refer to as ringing. More ringing, more cycles, less ringing, less cycles per pulse. Did that make sense?
Yes.
Good. 268. Now this question is more like a book, so let's see. So, okay, two ultrasound system produces acoustic pulses. Do we have names for the systems? Okay, they're just system 1 and 2. Okay, so system number 1 has, okay, yes. It has a wavelength of 0.5 millimeters. And it got 4 cycles per pulse. And okay, it has a pulse repetition period. No, it has a pulse repetition period of 1.2 milliseconds. Clear? Now the pulses from system 2 have a wavelength of 1 millimeter. So yes, okay, here the wavelength is 1 millimeter. We have 2 cycles per pulse. And okay, as the pulse repetition period is 1.8 milliseconds. Yeah. Now, which ultrasound system will have the lowest numerical value of axial resolution? Now goes for the numerical value of axial resolution. The only 2 parameters that we need is the wavelength and the number of cycles. So we can mainly say, okay, this information here is irrelevant. Clear? Did that make sense? The PRP ladies would only had been as irrelevant information if they have asked which of these 2 systems here has the greatest or shallowest depth of image. Where we can mainly say as okay, then that will be this system here, 1.8 milliseconds, we'll be having the greatest depth because of a greater PRP, greater time between pulse to pulse to pulse to pulse. And this one here, where I have, okay, that's the lowest depth of image. Why? Because of a lower PRP. Or what we actually is okay, just need to as okay calculate our axial resolutions. All the numerical values for the axial resolutions is going to be your wavelengths and your number of cycles. So for us, okay, system number 1. Now we have 4 millimeter, or we have 4 cycles. And each cycle was half a millimeter. So in this case, as okay, system 1, what do we get? We can make it as okay that our SPL is 2 millimeters, which means okay gives us as okay the numerical value is going to be equal to 1 millimeter. Yeah. Now, if you go for system 2, what do we have? We had 2 cycles, and each cycle was 1 millimeter. So what does our SPL spatial pulse length becomes? The 2 millimeters. And okay, we can make it okay, just divide that by 2 as well. So it's okay, the numerical value for this system here also becomes 1 millimeter. So as a matter of fact, yes, okay, both of these systems have the same axial resolution. If that makes sense.
Yes.
Okay. So you really have to say is okay, which information is relevant and which information here is irrelevant. Because okay, somebody might have been tempted to just okay, multiply these 2 numbers here. And say, okay, as system 1 had a lower numerical value. I had to ask about higher. That's okay, I've done the same calculation. So okay, this system here will have a higher axial resolution. Or numerical value of the axial resolution. So here it's okay, both of them have the same. Because it comes out to 2 millimeters, 2 millimeters. Where this factor here was made as okay, that's going to be determined by it's okay, the depth of your image. And I showed you the relationships. If you want to, okay, know the depth of your reflector, you can make this okay, that says okay, I don't, that's okay, multiply. That's okay, sorry, that's okay, we'll divide 1.2 by 13. Oh no, 1.2 is okay, it's okay. Or 100 divided by 13. That will give you okay, the depth of image in centimeters. Okay. But okay, let's not make it more complicated than it is. Okay, question number 269. Now, which transducer has the best exit resolution? Fine, okay. So you should already have, yes, okay, foreseen that, okay, this kind of questions here will come. Clear? Especially as, okay, when we said, okay, yes, thing that was going to just, okay, give us the best exit resolution was the highest frequency. And we can say, okay, lowest ranking. Clear? Now, as okay, what remains is I can say is okay, we have as okay, 4 examples. So as okay, the one that we need to look for is which transducer has the lowest ringing, which is going to be as okay, the lowest number of cycles per pulse. And okay, as a higher frequency. Both of that will give you, okay, will give us the best. Now we just, okay, easiest way, use the exclusion. So the first thing that we have is, okay, is number of cycles. Okay, so 2 is, okay, numbers we have is, okay, it's 4 cycles and 2 cycles. Where do we have 2 cycles? A and D. And 4 cycles, that's okay, that's B and C. So these 2 here are out. Because what we are looking for is the lowest number of cycles. So yes, okay, now between A and D, we have to look for the one with the greatest frequency, which is E and D, which is E. Because that is, sorry, 4 megahertz. D was 2 megahertz. So it becomes the system A, which has, okay, has lowest number of cycles. And yes, okay, the highest frequency. That will give us the best exit resolution. Clear? So question 270 is pretty much, okay, as just the opposite. Because it says, okay, which of these will have the worst exit resolution? Is that clear? So for worst exit resolution, yes, okay, what we mean is, okay, we just need is, we can say, okay, greatest number of cycles and the lowest frequency. Did you ladies get that?
Yes.
Okay, so again, yes, okay, the same mechanism. Yes, okay, exclusion method is the easiest way to, yes, okay, answer these type of questions here. So yes, okay, you may, yes, okay, we just exclude the one with the lowest number of cycles, which is going to be, yes, okay, again, we have 2 numbers again, 2 and 4 cycles. So 2 and 4. Where do we have 2? Again, it's okay, A and D. Where do we have 4? B and C. So right after directly, you can exclude these 2 here. And now, yes, okay, between B and C, yes, okay, you just have to look, okay, which has the lowest frequency. Okay. So B was okay as 4 megahertz. And C was 2 megahertz. So it becomes system C. Because greatest number of cycles, which is 4, and lowest frequency. Did that make sense? Okay. Now, please keep in mind, guys, okay, a similar question, okay, yes, because again, a similar kind of transducers can be given. But yes, okay, they may ask, this one here is, okay, yes, lowest numerical value of, because that's okay, ER, or any other, yes, okay, longitudinal, range, radial, or depth resolution. Or yes, okay, because that's okay, the worst exit resolution can also, yes, okay, be, yes, okay, the highest numerical value of, yes, okay, these resolutions here. Is that clear? Yes, girls.
Yeah.
Yeah, okay. Question 271. Now, two ultrasound produce pulses. Okay. As we just says, okay, let's just okay, say that we have two systems. Here, say 1 and 2, that's fine. Now, one pulse is 0.4 microseconds in pulse in duration. Like what we actually have been given here is going to be as okay, the pulse duration. So one has okay as a 0.4 microseconds pulse duration. And the other has okay as 0.2 microseconds pulse duration. Now, what they mainly say here is okay, as which of these two here is going to just okay give you the best radial resolution. I just give my radial resolution, yes, okay, just for the also, yes, okay, or called exit resolution. And some of you may go and say, well, okay, can't be determined. Well, it can. Just if you keep in mind that, okay, yes, pulse duration is directly proportional to spatial pulse length. Did that make sense? If you still don't, well, okay, let me refresh your memory. Pulse duration was number of cycles. So what was your spatial pulse length? Number of cycles. So here is okay, we multiply that by the period. And here is okay, we multiply that by the wavelength. But we also, yes, okay, know, and we already, yes, okay, know that, and we talked about this relationship that, okay, as period is directly proportional to wavelength. Which may mean that, okay, yes, where we have, yes, okay, we can say, yes, okay, a greater period or greater pulse duration. Now, mainly mean that we also have, okay, a greater spatial pulse length. Did that make sense? Did that make sense, girls? Whereas, okay, when we have, okay, as a lower period, or you can say, okay, lower pulse duration, sorry. We actually, as okay, indirectly say, okay, we have a lower spatial pulse length. So that's where you can make it says, okay, this system here is okay with a lower spatial pulse length. Actually, we have okay at the lower numerical value of the as okay radial resolution or axial resolution. Where that lower numerical value is okay will give it the best axial resolution. Whereas this system here made it okay due to the greater period or pulse duration, sorry, will have okay as a greater spatial pulse length. And that will actually cause it to have okay as a greater numerical value of our axial resolution. But actually is okay will lead to is okay that this axial resolution here will be poor or the worst or bad compared to the other one. Clear? Now, although as okay in this chapter here as okay, pulse duration wasn't mentioned. But you should have known that from yes, okay, the good old days. The pulse duration and spatial pulse length are directly proportional because as okay, both of them have okay as this common factor here, number of cycles. Yeah, okay, for period duration is just going to multiply by the period. How long is it that it takes one cycle to complete? Which is going to be as okay, directly proportional to as okay, the physical measurement or length of the wave, which is the wavelength. Did you girls get that? Clear? Now, an option that could have been as okay, not determined, has been had they not asked about the axial resolution or radial resolution, but used any other words such as lateral resolution, angular resolution, transverse resolution, and or is okay, the azimuthal. Then we really can't determine which of these two systems here is going to have the best or worst of these because these resolutions here were determined by something else, which was the width or the width of the beam. Clear? Did you girls get that?
Yes.
Good, buddy. Question 272. So what is it we have here? So, okay, a sonographer, that would be any of you, is performing a study on a patient and desires superior depth resolution. Now goes probably as okay as we go into the options here, as okay, you will see why they ask or what they use the word depth resolution in the question. Clear? Now, which of the following systems, oh, sorry, let's see, which of the following changes would create such a system? Now, depth resolution, that would mean it's okay, just another name for our famously known as okay, active resolution. And what do we want to achieve? A better axial resolution or depth resolution. Now, ladies, option 1 says a higher frequency. Is a higher frequency as okay going to give you a better resolution or depth resolution? Yes. Shorter wavelength. Well, pretty much okay, it's just the same as okay as you were. That's also going to give you okay a better resolution or depth resolution. Clear? Question now, option C. Fewer cycles. Now, there's fewer cycles could also as okay, be as okay, we could say as okay, less ringing. Okay, which is mainly as okay, just option D as well. That goes okay as less ringing. So C and D actually is okay, means the same thing, just in different wording. Likewise, we can say as okay, A and D would mean the same as well. So here is okay, all of these is okay, will lead to is okay, a better axial resolution or depth resolution. Okay. Yeah. Okay. Now an answer which would have been wrong in this instance here was, could have been. Okay, let's see. Okay, this one. If we increase the depth. Yeah. That increasing of depth was not going to just okay give you a better depth resolution. So that would have been false. So you can begin with okay, these options, and they might have said, okay, which of the following might not give you okay, a better depth resolution. And people who don't know the difference between depth resolution versus depth will probably not have chosen this one here. Because okay, greater depth, greater is always better. Yeah. Did you girls get that?
Yes.
Okay. So that's okay. In this question, that's okay. All of the options, okay, will actually that's okay, give you a better depth resolution. Question 273. Again, it's okay, true or false. Now, the higher the frequency of cycles within a pulse, the lower the numerical value of the axial resolution. Okay. Now girls here is okay. What they mean is okay. They want to do was confuse you with cycles within the pulse. Okay. That says okay. Greater frequency of cycles in the pulse. This does not mean more ringing. But mainly it's okay, it's just all about it's okay, a greater frequency. Is that clear? So here
Yeah.
is okay, this, some people may think of this as okay, meaning it's okay, more ringing. And choose the wrong answer. So it's okay, here it's okay, the greater frequency of cycles in a pulse. Mainly it's okay, only will refer to as okay that you have a greater frequency. Where a greater frequency leads to a lower numerical value of your axial resolution. Yes, so that is true. Whereas if you took that okay as greater frequency of cycles in a pulse meant greater, more ringing. Okay, you say okay, that will lead to as okay a greater numerical value. And that greater numerical value will not lead to a better resolution, and you might have chosen the wrong answer because you misunderstood this whole thing here as more ringing. Did that make sense?
Yeah.
Question number 74, 274, should be more correct. So shorter pulse, the shorter pulse length, the better the picture. Okay, we can say, okay, shorter SPL. Greater resolution or better resolution. That is true. Clear. Had this said the opposite. Greater pulse, lower resolution. That has been true as well. Clear. Had they said greater pulse, greater resolution, that would be false. And onwards. Lesser pulse, shorter pulse, poor resolution, that will be false as well. Clear? So yes, okay. I can only say yes, okay. Look out for yes, okay. Tricks in the question like, okay, yes, confusing resolution with the numerical value. Because greater numerical value will be yes, okay, lower resolution. Okay, girls. Okay. And what do we have then? Now we have some questions that's okay at the end. Okay, sorry. I can give it out in written. So yes, okay, we can maybe just okay go and say it's going to be okay from page 492 to page 496. Or we can say it's okay from question 328. To question 349. So approximately is okay, some 19 questions. Now girls, take your lunch break and try to, yes, okay, go over these questions here, look at them, try to answer them on your own. And when we come back around 1 o'clock, we will just, okay, look at these questions here together and they are similar games, okay? Sounds like a plan?
Yes.
Okay, so see you ladies around 1 o'clock then. Welcome back. So okay, ladies, let's see. Okay, so we are on page 492. And this is going to be, okay, question 328. So that's okay. The next series of questions is mainly about lateral resolution and focusing. And we can mainly say, okay, especially that's okay when we talk focusing, that's going to be okay, directly related to this, okay, the beam of ultrasound. Okay. And so is your lateral resolution. Now, question number 328 reads, the focus of an ultrasound beam is the location where the now goes by now. You should maybe just okay be able to just okay say what that's going to be. So the focus of the beam, that's going to be the location where the beam is at its narrowest diameter. Clear? That could have been one option. But the option that we have is the beam is broadest. No, that's the opposite of what we just said here. Had optimum transverse resolution. Our transverse resolution was just the same as your lateral resolution. And at the focus, that's where that is going to be as okay, best transverse resolution, also known as lateral resolution, also known as angular resolution, also known as okay, as azimuthal resolution. The frequency is highest. No, that's not the narrowest point of your beam. Clear? Okay. the finest depth resolution is obtained. That is false. Okay, as well. So the one is going to be as okay, where we have the best of okay as the transverse resolution because of the narrowest width of the beam. Did that make sense? But again, yes, okay, as I said, please make sure that you know that okay, as your lateral resolution goes under yes, okay, different names. Okay, and which goes for what? Question 329. Lateral resolution of an ultrasound system is primarily determined by the, and we says, okay, lateral resolution is equal to the width of the beam. That's what we have as option A. Okay. Now let's just look at okay, why other options are wrong. Length of the ultrasound pulse. Now yes, okay, we can say okay, length of ultrasound pulse. That would mean yes, okay, determine yes, okay, our exit resolution. So what's option yes, okay, so what we could say is okay, duration of ultrasound pulse. Indirectly yes, okay, still yes, okay, determine yes, okay, your exit resolution. Or none of the above. Okay, now please keep in mind, guys, yes, okay, this is the option width, which may remain yes, okay, be yes, okay, if we said this was the beam in a cross section at any point, let's say here. This dimension would be the width. And that is going to determine, yes, okay, your lateral resolution. Okay. Later on in a later chapter, we may yes, okay, say it's okay, the height of the beam. Now, goals that is going to determine it's okay, that third spatial resolution that we talked about are going to, so that we briefly mentioned, which is elevational resolution. So here has a height of the beam, then that would not have been an answer for your lateral resolution as well. Clear? So it has to be as okay, the width of the beam. That will determine your lateral resolution. Did that make sense? And that's why they say as okay, objects that are going to be side to side. Because that's okay, one will be on the left side, one will be on the right side. These two, yes, okay, be displayed as two separate reflections or structures. Well, yes, okay, indicate yes, okay, a good lateral resolution. Okay, because the width of the beam is lesser than or equal to the distance between these two structures here, which are side by side. Did you ladies get that?
Yes.
Okay. Question number 330. Now, two ultrasound system produces. Okay, let's see. It's okay. Two ultrasound system produces acoustic pulses. Okay, good. They just tell us that these are imaging transducers or systems. Right? Okay. Okay, one pulse is, so we can say, okay, we have, okay, we can just say, okay, system A and system B. Just to have something to refer to. Now, one has, okay, one pulse is 0.4 microseconds. and the other one is 0.2 microseconds. And what was that? That was mean it's okay because that's your pulse duration. Okay, now which pulse is likely going to provide the best lateral resolution? Okay, now goes here. We don't really have the information that we need. What we needed to know was okay for your lateral resolution was because it says okay the width of the beam. And we got any information of okay as a width of the beam because it says okay lower width. That's okay, that will be as okay a better resolution. Or because it says okay a greater width. That will help me as okay poor lateral resolution. Since here is okay, we don't have any of that information. That's why okay, yes, it can't be determined. Okay. It would have been a different question, it would have been a different thing had they asked us about, well, same data, I think we already had that, and said, well, okay, yes, exit resolution. So which one will have a better exit resolution? Shorter pulse would be better. Or because it's okay, the longer pulse here would have been a poorer exit resolution. Did that make sense? So here is okay, we don't have the info to determine. Clear? Did you girls get that?
Yes.
Yes.
Good. Okay. 331. One of my favorite formats. True or false? Or is our statement here true or is it false? So yes, okay, pulse duration does not profoundly influence the lateral resolution. That is true. Because we can mean it as okay, does pulse duration is yes, okay, either a high pulse duration or let's say yes, okay, low pulse duration. Is that going to have any effect on your lateral resolution? No. So that's okay. Why? Because these two here are not related. Clear. So that's okay. That's how we can say the pulse duration is okay, whether it's a great pulse duration or a shorter pulse duration, is not going to cause any effect on your lateral resolution. And it asked the same, yes, okay, given the same info and asked about your exit resolution, then yes, that were affected. Question number 332. For two ultrasound systems, okay, good. So we have two ultrasound systems, okay, and we can say that one is system G and P, okay, what the? So we have system G as in good. We have system P as in penny. Good. So two ultrasound systems have near zone focal length, have near zone lengths of 8 centimeters. So we can say, okay, the near zones for both of these systems here is 8 centimeters. This near zone could also be referred to as okay as focal depths or lengths. Did that make sense? Now, the next thing is that it says, okay, at the focus. At the focus. Now, what should we get from the at the focus? That beam is narrowest, right? That's pretty much okay. That's the info that we get from that, which is going to be as okay at a depth of 8 centimeters. Okay, but what they mainly say is okay, the lateral resolution of system G's lateral resolution is 3 millimeters. That's okay. The lateral resolution of system G is 3 millimeters. And that of system P is 5 millimeters. Did you ladies get that?
Yeah.
Okay, where we can mainly say as okay, what that mainly mean that okay, as at the depth of focus or at a depth of 8 centimeters, this beam here is okay, is having a lower width, where we can say as okay, this beam here has a greater width. Okay, and now the main is okay, just says okay, which system will produce the higher quality pictures at the foci? Now again, as okay, higher quality is probably as okay, a little bit as okay off term to use, but we can say as okay. Yeah, okay, what we're looking for is okay, as the better lateral resolution. Where? At the focus. Where your focus at a depth of 8 centimeters. What are your widths? 3 millimeters, 5 millimeters. This lower width here is going to mean that we have a lower numerical value. This greater width here is going to mean that we have a greater numerical value. And what we said was the greater the numerical value, poor resolution. Lower numerical value, meaning the lower width, is going to mean that that's going to be the one with the best lateral resolution. Did you girls get that?
Yes.
Clear? Okay. Now, girls, you could have been given us okay, we can say it's okay, the same information, but if they asked you, we can say it's okay, system, focus at 8 centimeters, focus at 8 centimeters. Okay. We can say it's okay, at focus is 3 millimeters wide, 5 millimeters wide. Okay, that's the information that you've been given. But then they may have asked you, it's okay, which system of these two here could have, it's okay, because it's okay, the biggest PCT. Yes. Which system will have had the biggest piezoelectrical?
The 5 millimeters.
The 5 millimeter one, right? Okay, because we come in and said, okay, for this one here, it's okay, the size of the PCT would have been, because it's okay, 10 millimeters, where for this one here, it would have been 6 millimeters, right? Did that make sense? Good job, Shaq. Next. When using, yes, okay, so true and false. So question 333. Okay, what a number. So it's going to be, okay, true or false. So when using standard ultrasound imaging instrumentation, the lateral resolution has a higher numerical value than the axial resolution. And that is true. And that's okay. That's why it's okay when we compared axial resolution versus lateral resolution. Versus as okay, what I said is okay was elevational resolution. For main standard, yes, okay, system, what you mainly will see is okay, your spatial pulse length is always going to be as okay, be very, very small. It can mean it says okay that the beams width is going to be great. And what you will see in most yes, okay, transducer is that okay, yes, the beams height is going to be as okay the highest, which means okay leads to yes, okay the numerical values of each of these. Where it says okay the lowest numerical value is best resolution. Greater numerical value is, well, okay, we can say it's okay bad, and okay as the highest numerical value that's going to lead to the worst resolution. So comparing as okay these three resolutions here, as okay elevate axial resolution is always going to be best, lateral a little bit more poorer than that, and okay as elevation will going to be as okay the worst. By here as okay they mean as okay just compared these two. So maybe as okay as per standard is okay. Half of your spatial pulse then is always going to as okay be a smaller distance than okay as the width of the beam, which may call okay this have a lower numerical value than your lateral resolution, which may call okay they have a better axial resolution. The axial resolution is always going to be better than the lateral resolution. Did that make sense? Did that make sense?
Yeah.
Yes.
Okay. I think I asked you ladies to just okay copy down that that slide that I made that other day. Maybe start talking about resolutions. If not, you can always go back and okay, just look at the Zoom session if it allows you. Now let's just go to the next question. 334. And okay, yes, we're going to be thrown around at the alphabet. So we have again, yes, okay, two systems. You can say system Q and system H. Okay, so yes, okay. And okay, yes, again, yes, okay, they have near zone lengths of 8 centimeters. What do we mean by yes, okay, near zone lengths? That's what we also could call as okay, focal length. Or focal depth. And in this case, that's okay, it's going to be as okay, the same. 8 centimeters. I don't know what this book has about is okay, focal length and 8 centimeters. Okay, good. Now let's just look here. Now at their foci. So we can say, okay, the next thing that we're going to talk about is going to be, okay, at the focus. What would I mean? At a depth of 8 centimeters, right? Okay. Okay. Now system Q has a lateral resolution of 3 millimeters. Clear? Which may mean, okay, the beam is 3 millimeters wide. And system H has a lateral resolution of 5 millimeters. Which system will correctly display two structures that are at a depth of 8 centimeters? Okay. Okay, which system will correctly display two structures that are at a depth of 8 centimeters? The objects are side by side and are 4 centimeters apart. Upon 4 centimeters apart. So what they mean is, okay, say of these two systems here, at a depth of 5 centimeters or 8 centimeters, which is the focus, where one has a beam width of 3 millimeters. And the other has a width of the beam at the focus, which is 5 centimeters. Which system where yes, okay, display two structures which are 0.4 centimeters apart, side by side. So what they mean is, okay, we have two structures which are going to be as, okay, at a distance of, they're side by side, and this distance here is 0.4 centimeters, which mainly will mean that, okay, at the distance is 4 millimeters. Now we can mainly as, okay, just place this and say about, okay, this and this. Because yes, okay, this distance is, okay, was 4 millimeters. Or 0.4 centimeters. Where what we have here, this and this distance will have been 4 millimeters. So the system that's going to as, okay, give us, we can say as, okay, the best lateral resolution is going to be system Q. Why? Mainly because we can say that, okay, as the numerical value of lateral resolution, which was the beam's width, that was lesser than the distance between the two structures, which were side by side. So that gives us, okay, as a good lateral resolution. All of these two systems would be, that's okay, the best lateral resolution. Did that make sense? Whereas for system H, you could may say, well, this was your two structures, but they may as, okay, actually show up like something like this on your image. So you can't say that we had, okay, as two separate structures, but they actually just, okay, look like, okay, as being one big mess. Did you ladies get that?
Yes.
Now let us just look at question 335. Because that means okay, going to look at as some similar things here, it's okay, but just in a different way. And as a matter of fact, it's okay, it even starts the question definitely and saying it's okay. The lateral resolution of an ultrasound system is 4 millimeters. So we can say, okay, the lateral resolution of a system is 4 millimeters. What would that mean? What does this lateral resolution here mean? Beams width. Now, two structures are separated by 3 millimeters and lie side by side in relation to the sound beam. So we actually say, okay, if we had a beam, and we could say, it's okay, that is lateral resolution, which is the width of the beam, was 4 millimeters. So we can say, okay, the distance from here to here, this distance measures 4 millimeters. Okay. Now we have two structures that are separated by, yes, okay, 3 millimeters, and they lie side by side. So we have two structures. But the distance between these two structures here is going to be, yes, okay, 3 millimeters apart. Although, yes, okay, they lie side by side. In relation to the sound beam's main axis. Good. What will most likely appear on the system's display? So yes, okay, if that was the case, what would we see? Would we see two weak echoes 4 millimeters apart? No. Because, okay, they were 3 millimeters apart. Yeah. Do we see two bright echoes 3 centimeters apart? No. Do we see one echo? Just as I said here. When the width of the beam was greater than the distance between the two structures. Yes, okay. Two structures, 3 structures, it doesn't really matter. What that mainly produced was only as okay, one echo. So that's mainly as okay what we see here. So these two structures, yes, okay, when they're going to, yes, okay, be reflected back, all this, okay, they are side by side, but they're just going to show up as one echo. And that will mainly mean that, okay, in this case, we have a poor lateral resolution. Why? Mainly because we can say, okay, the numerical value of the beam, or the numerical value of your lateral resolution, which was the beam's width, that was greater than the distance between, yes, okay, these two side-by-side lying structures. Did that make sense?
Yeah.
Okay, so for us to find this, okay, how had I have to how you guess it's okay. Good lateral resolution. In this case, that's okay, we can say, but if the diameter of the beam was 3 millimeters or less than 3 millimeters, that will give us, okay, yes, a good lateral resolution for these two structures here, which would have been 3 millimeters apart. Okay. Did that make sense? Then we could at least says, okay, we will see as, okay, two echoes 3 millimeters apart. Did that make sense? Did that make sense, guys?
Yeah.
Yes.
Okay. The brightness, okay, that's going to as okay be dependent upon as okay the actual nature of the echoes. That's okay. What make up these structures here? Okay. Okay. Or we will actually it's okay see two echoes that were had been 3 millimeters apart. And that one says, okay, well, okay, they are 3 millimeters apart. We see them as being 3 millimeters apart. So that's going to say, okay, you can say everything about this one here is, you can say, okay, a good lateral resolution. Did you girls get that?
Yes.
Good. Question 336. So again, yes, okay, true or false. When using an ultrasound instrument typical of today's imaging system devices, a higher frequency transducer is likely to mildly improve the system's lateral resolution. Now, just think of it in this way here. That we said, okay, as frequency. Sorry. OMG. Or we can say that will be true mainly because it's okay, higher frequency actually will lead to yes, okay, lower beam divergence. Which may mean that okay, as in the far zone, the beam will actually as okay keep as okay maintain a narrow width for a greater distance, which means okay will improve yes okay the lateral resolution in the far zone. Did that make sense? So that relationship that we did in yes okay your chapter 9, if you guys remember. The focal depths directly proportional to frac and diameter. And then we says, okay, beam divergence was inversely proportional to yes, okay, the frequency. And also yes, okay, inversely proportional to the diameter. So it's made as okay, there's this relationship here that they are asking about. So a higher frequency as okay will cause lesser divergence of the beam in the far zone. Because it's okay, they are inversely proportional. It says okay, a higher frequency, lesser beam divergence. Which means okay, the beam remains narrow for a longer distance. Did that make any SENSE?
Yes.
Good, but Okay, goalies 327. No, 337, sorry. Again, true or false? When using an instrument typical of diagnostic imaging, higher frequency transducer improves the axial resolution. Is it true to say that, okay, higher frequency transducers leads to a
No.
improved axial resolution? Is that true or false?
Oh,
True.
Pump it up.
True.
It's true, exactly. We've just been talking about that, okay, as before the break, right? Because again, what would this higher frequency lead to indirectly? As okay, we can say, okay, a lower wavelength. Lower wavelength, yes, okay. Lower SPL, which will mean lower numerical value of, okay, this axial resolution. And the lower the numerical value, that's okay, the better the resolution is. Good job, Jen. And some of you may be scratching your heads and say, where does axial resolution comes in questions about lateral resolution? Okay. Okay, ladies, let's see, 338. Now, what will lower the value of an ultrasound system's lateral resolution? What will lower the value of an ultrasound system's lateral resolution? Decrease the number of cycles in the pulse? No, that has nothing to do with your lateral resolution, right? It will only, okay, affect the axial resolution. Or we can say, okay, improve your lateral resolution. We can say as okay, increase the effective or increase if the effective damping material. No, that's okay. That will again as okay, only improve your, or we can say as okay, reduce the frequency. Right? We can say increase of the pulse repetition period. That is completely out of question here. Because okay, increasing your pulse repetition period is just going to just okay, increase your depth of image. So it has nothing to do with whatever they're asking. Using an acoustic lens. No, it's okay. We probably as okay talking about it's okay, focusing now. Clear. And what was one of the means by which as okay we could bring the beam into a focus? Was okay, that's by a lens. And by so, yes, okay. You can say, okay, improve your lateral resolution. Or as they may asking this question is okay, which of the following is okay, will lower the value. Or what they mean is okay, just mean by value here is the numerical value. So how do we reduce the value of the numerical value? That's okay. enable the beam to focus. So the only mechanism that's okay mentioned here that will actually help us focus is as okay if we use the lens. What do we call this kind of focusing where we use a lens? Yes, girls. What do we call the kind of focusing where we use a lens?
Phase?
Huh?
Can it be, I'm guessing, so I'm pretty sure I'm wrong.
Better be wrong than
Phase?
saying no. I can't hear, my dear.
Phase?
No.
Okay.
Phase was electronic.
Focused?
Wow, okay. Focus is focus.
Sorry, it's fixed, right?
Huh?
Is it fixed?
Fixed. Now, when we say fixed, then okay, yes. But we still, okay, my question is still yes, okay, not answered. Because, okay, when we say fixed focus, that's okay, due to, yes, okay, using a lens. What would that be?
Is it
It can't be-
external fixed focus?
Pardon me?
Is it external fixed
It's
focus?
external, right? Okay, exactly. It's external. So yes, okay, I guess the following questions are main, yes, okay, going to be focused on focusing. Clear? Let's see, okay, 339. Which of the following focusing techniques is different from the other? Now we say lens. We already says, okay, that was already called external. But we can say, okay, it's still going to be, it's okay, fixed. We said curved crystal, or PCT as we may call it. That is actually, it's okay, what we call internal focusing. But this was still going to be, as okay, fixed. Clear? Then you see option C is fixed. And then option D, as in donut, is phased. That's the one that doesn't match any of these. Because what A, B, and C had in common is, okay, they were all examples of what we call fixed focusing. Did that make sense?
Yes.
It's, ladies, look at your focusing. You're going to be needing that during chapter number 12, which is just around the corner. $340. Which of the following techniques is external? It's going to be as okay, internal focusing. We already said that, right? Okay. Internal focusing. Which, okay, that's okay. In this case, yes, okay, was fixed. But now they specifically asked about is okay, the internal focusing. And that was when we had a curved PCT or crystal, which we also can call as okay, an active element. Clear? Had it said external focusing, which still was fixed. But in that case, okay, the answer had been lens. Clear. And electronic, yes, okay, that would be yes, okay, what you call phased or multi-focused. Clear? So we can go to 341. Now, which of the following technique is external focusing? Well, okay, you already answered that one. That's your lens. Okay. Yes, okay, had a curved lens in front of the PCT. Question number 342. Which of these terms means adjustable or multiple focusing? So what means, or what's going to, yes, okay, mean the same as multiple and or adjustable focusing? No, main is because they say mean. That is going to be, yes, okay, to be phased array. All those, okay, in this case, if we can mean, says, okay, the term array itself may be just enough to, yes, okay, say that it is multiple focusing. What does multiple focusing mean? That we are able to, yes, okay, we are able to, if we choose to focus at more than one depth. Clear? That doesn't necessarily mean that we have to, but we have the option. Okay, your car can run up to, yes, okay, 240 miles per hour. Have any of you ever taken it to that level? Have any of you ever tried to, yes, okay, give your car that much gas that it runs at 240 miles per hour?
No.
Or 360, whatever car you're riding?
No.
No, just because, okay, it is, you can doesn't necessarily mean that you have to, right? You will say, do I really need to, yes, okay, to run 360 miles an hour right now? No. So, or you can if you choose to. You may just have to pay the consequences then. Clear? Now, dynamic aperture, girls, that is going to be a mechanism by which it's, no, I don't need you to say anything. Wait, sorry. Okay, so dynamic aperture is okay. That's something that we'll come across in either chapter 12 or 14. Well, it has something to do with focusing, but we'll talk about that when we get to that point. Okay, harmonics is okay at chapter 17. A little R chapter. Not really is okay connected to any chapter at all. So that's okay, isolated fellow. And frequency, agility, or what the blue they mean from that. So the only one that makes sense here is phased array. Or even if it just said array, that would mean it's okay, multiple focusing. Question 343. Okay, which of these techniques is consistent with a variable or multifocusing? And again, yes, okay. Multifocusing, that has to be, in 99.999% of the cases, it is going to be electronic. We will in chapter 14 see that there is OKS. One exception, you still be able to just, okay, focus at multiple points, but where it is not electronic. And in that case, you can mean it as, okay, you don't really have a choice to choose. It will just focus at multiple points by itself. Pretty much, okay, it's automatically. Okay. Question 344. All of the following occur with focusing except from lower intensity of focus. Okay, see, that's the thing that doesn't occur at focusing. It's rather the vice versa. Because what did we have at focus? Smallest diameter. Or area, right? What does that mean? Greater intensity. Okay. We end up having a shorter near zone length. We had that as an option. As okay, one of the okay consequences. Okay, what occurs during a focusing yesterday. More compact focal zone. That the focal zone actually is okay, gets more compact. It may mean remains narrower. Okay, and a smaller diameter of the beam at the end of the near zone. What do you mean by the end of the near zone? That's the focal point. So what do you have at a focal point of focus? The beam's diameter is at its narrowest. So the only thing that didn't make sense here was, okay, we had a lower intensity at the focus. Is rather vice versa. Okay. Now, guys, we are mainly okay, just left with approximately 4 or 5 questions. Oh, that's okay. 1, 2, 3, 4. 4 questions. The last 4 questions. And what you can do is, or what I recommend you do is, if you haven't done it yet, then do it. Look at them, try to answer them. And okay, as if you are still in any doubt, we can always just okay bring that up tomorrow. Otherwise, tomorrow we're going to just okay be doing one of the super short chapters of this book here, chapter number 12. Okay, clear? So for chapter 12, please, ladies, make sure that you know what an amplitude is. Clear? What your 3 axes were, X, Y, and Z. Right? And what we mean by depth of image and its relationship to PRP, PRF, right? Okay. And focus. So these will be as okay some topics that I would like you ladies to have revised by tomorrow. Okay.
Okay.
So none of them are topics that we haven't done so far. Okay, ladies, have a blessed evening. Take care of yourselves and See you ladies tomorrow.
You too. Thank you.
You're welcome, dear.
Bye.
Bye-bye, dear.
I have a question.
Yeah, just a second, my dear. Okay, let me just